Okay, chapter 9 deals with torque and the conditions for static equilibrium for extended objects. So you can imagine you have a bolt, something like this, and you want to turn the bolt. What do you use? You use a wrench, right? Something like that. And how do you do this? Well, you apply usually some force out on the end of the wrench. And so your ability to either turn or not turn that bolt is determined by something called torque. And the way you calculate a torque is as follows. There will be some distance between the pivot, that's the point that your object may or may not rotate about, and where you apply the force. We'll call that R. That's a radial distance. Why? Because as you turn the wrench, you'll make a circle. Okay, and then there's some size of the force. Okay, both those things matter, and you know that intuitively because you can try pushing a wrench at different positions and see what kind of results you get. The further away you push, you'll notice the greater the result in terms of your ability to turn a bolt. But that's not it. It also matters in what direction you apply your force. So I can apply, for example, a force this way or that way, and that's not going to rotate the bolt at all, even if it's the same size force. So it's not as simple as just the size of the force, it's also the direction it's applied. And the direction that matters is perpendicular to the radial line. So only the component of your force perpendicular to that radial line counts in terms of producing torque. So putting this all together, we have this new thing called torque, and it's equal to the size of a force applied perpendicular to the radial line multiplied by the radial distance. You can also do this in a different way. You could say if this is the force I applied and it goes this direction, you can get something called the moment arm, I believe, which is R perpendicular effectively, which is then that. And necessarily through trigonometry, this is equal to this. And in either case, notice that the two angles I just drew are necessarily the same angle through geometry. This is equal to the force multiplied by the radial distance multiplied by the sine of that angle, where that angle is the angle that lives between the direction of the radial line and the direction of the applied force. So that's how you calculate a torque. And the other part of chapter 9 then is that if tau net is equal to 0, object doesn't rotate, or doesn't angularly accelerate, I should say. We haven't gotten to that word yet. But if it's at rest already, it will remain at where it rests. Which is to say it will not begin to spontaneously rotate if it's not already rotating. Torque is a type of vector, but in this case, it can be either clockwise or counterclockwise. Where this is the positive direction and that's the negative direction. In this case, we are attempting to apply a positive torque because if this bolt were to rotate, it would rotate that way. Okay.